Thank you very much for the introduction, Professor Yoden. It is a great honor to share with you what we are doing at our institution. So I would like to say thank you to Kyoto University and Inamori Foundation. Please look at this picture. So this is the picture of the vessel, which is called a Chikyu. Chikyu means earth in Japanese, and this vessel got the name as Chikyu. And today I am going to talk about our research using this vessel. But before that, I would like to give you a background to explain how I became involved in the construction of this vessel. I am the director of this institution, therefore let me first give you the overview of the organization. I am kind of coerced to explain my organization every time. So our institution is under the umbrella of the Ministry of Education, Culture, Sports, Science and Technology, and we have different sites: Kochi, Mutsu, Yokohama, Yokosuka, and we have different vessels. One is Urashima and Aurora Vehicle and Robotics, and also Chikyu and Chikyu simulators. This is the supercomputers. We have large facilities to conduct research on the geo-environment, and we would like to contribute to the survival of human beings going forward. And I am a geologist, therefore when it comes to the Earth, I am interested in inside the Earth itself. But one big framework in this field is a continental drift, seafloor spreading, and plate tectonics. And our seafloor drilling plays a very important role in the research of these areas. About 100 years ago, the Alfred Wegener came up with a theory, which is a continental drift. And if you look at the Earth, just both sides of the continent in between the Atlantics, their shape of the continent are very similar. That's why he came up with an idea, and they looked at the distributions of the remains from these 300 million years ago. He came up with this idea that in 300 million years ago, there was a supercontinent. This is quite an interesting theory. And the researchers in Southern Hemisphere, the Southern American researchers and also the African researchers, they accepted this idea, but researchers in Europe, they didn't accept this idea, so they basically rejected this idea. And 50 years later, after the World War II, the marine research began, and then in the middle of the Atlantic Ocean, they identified the mid-Atlantic ridge, just in the middle of the Atlantic Ocean. And because of the advancement of the technology of sonar, they were able to find the mid-Atlantic ridge. The discovery of the mid-Atlantic ridge led to a seafloor spreading hypothesis. And Alfred Wegener pointed out that a continent was divided. At the same time, the new seafloor was developed. So this is the key point of the seafloor spreading hypothesis. And Alfred Wegener looked at this sphere following the granitoid layer. But in this seafloor spreading hypothesis, the continent, the new seafloor is born out of the thrust from the thrust of the magma from the seabed, and how it can be proved. And then a global challenger vessel was launched in order to further advance this series. And here, as you can see, there's a tower like this. This is for a bowling and drill pipe is dropped from the vessel, and it can drill the seafloor. So this is a seafloor drilling vessel. This began in 1968, so it's about 50 years ago. So seafloor spreading hypothesis research itself began with the global challenger. And the result was so significant. So here you have the Mid-Atlantic Ridge and South America and African continent. And those are the drilling points. And this is the distance from the axis of the ridge. So 1,200 kilometers, 1,600 kilometers from the ridge axis. And then they looked at the plankton fossils to understand the age. And for example, here like 80 million years and 70 million years and 30 million years. And those research results are plotted like the graph that you can see to the right. And the longer distance from the edge means that the older layer of geology. So this was proved by the seafloor drilling with the global challenger. And the seafloor spreading hypothesis unlike the plate tectonics, you see here is magma. So magma is the thrusting out, and it's caused a lithosphere, new plate, and this new plate move little by little. And if it keeps expanding, then the surface will also be expanded. Therefore, this plate will be subducted in the trench. So from the seafloor spreading hypothesis to the plate tectonics, the geoscience, the Japanese research didn't much contribute to these theories because these are all the marine science. But Japan Islands are located close to the trench. So this is a subduction zone. So Japan is located just next to the subduction zone. So after plate tectonics theory emerged, we in Japan decided to look into the mechanism of the plate subduction zone because we are closely located to this kind of subduction zone. And my first research concerns the plate subduction zone. What is happening in this zone? So this is a Japanese archipelago, and there are 4 plates. This is quite an active area for a plate tectonic perspective. And in 1970s, towards the end of 1970, when the plate tectonics was already demonstrated as a variable theory, I was with the Kochi University, and I was involved in the research of sedimentology. And with the Kochi University, being a teacher at the university, there is always some hierarchical structure, and then I came from the Tohoku University, and I just a call from my supervisor, Mr. Taira, why don't you come to Kochi University? And I couldn't say no. So there's very strong hierarchy. Therefore, there was no option for me to say no. That's why I moved to Kochi University. And at the Kochi University, Professor Kato, who called me to the Kochi University, and he had a very high confidence in myself, and he allowed me to appoint 2 additional assistant professors. And also at the Kochi University, that Kochi University didn't have much budget. I was with Kochi University for 8 years. We were not able to attract any budget from the government scientific body. So we have only like 400,000 a year from the university itself for some kind of subsidy. And our students, they are very good people. They are very hardworking, and they are very passionate. They are very good students. So I started research with those students, and what we did in the beginning, that I just bought aerial pictures, and just we brought some hammer, and we went to some geological area to excavate. And also after those exploration, I needed to buy drink for my student. Therefore, I spent a lot of money for drinking with students. And this is Kochi area where my university is located. And this geological areas is quite unique. For example, compared to Grand Canyon, the layer of different geological strata, this kind of regular understanding cannot be applied to this geological terrain, and it is extended from Okinawa to Kanto, so it's quite a large geological terrain, but there are almost none in terms of the fossil findings. So there is such an extensive geological terrain, but we don't have much information about this terrain. That's why we began the research for this terrain. This yellow area is the a black one is the melange layers, so various rocks mixed up, and then these yellow areas is a sandy layer. And as you can see, this is folded sandstone, and this is myself in this picture. And this is quite a typical folding structure. And here, in just between sandstone beds, there was a pillow lava. So this is a pillow-like lava, as you can see. And this is the hammer used. So this is a waveform, 2 millimeter square. And this is the thin sections of the mineral. And the plate lava presence means that according to the plate tectonics or the seafloor spreading, the magma that thrust out is included in the layer of Kochi. And chert, it's very hard layer can be also found. So if you look at the thin section photos, so those are all the square shape, the plankton, which is called the radiolarian. So in the beginning, after this discovery, we conducted various researches on those different type of rocks, and of course there are different sizes and scales. For example, this one is chert and sandstone and volcanic ash. So those were discovered in different scales, like a mountain scale or very small scale, but they are very randomly coexisted. So there's no layer of geology. There's no typical geological strata. So in order to understand these layers, of course, the fossils were required. And my collaborator used our method to extract those fossils from chert and those rocks. And student at Kochi University. So some of their thesis, actually I requested requested student to extract 1,000 radiolarian, and then they usually able to extract like 100 those fossils, and I took advantage of a cheap labor of my students because they are free basically. So I just simply gave an instruction to extract those fossils. But anyway, we were able to extract those radiolarian fossils. Then by analyzing those fossils, we were able to understand the geological layers. So up until 130 years ago, there were pillow-like basalt layers, and also you have nano limestone. You have the layer of chert as well. So by looking at these fossils, we were able to come up with the geological strata like this. So 130 million years ago, the geological layers used to be there at close to the equator, and currently it's around 30 degree compared to the paleo latitude. So there's distance of 3,000 kilometers. So what it means is that 130 million years ago, those a new pillow lava was generated, and it took 60 million years to move 3,000 kilometers to form the geological strata I am talking about at the Kochi areas. So based on the result of the fossil research as well as the geological research, we were able to demonstrate the validity of seafloor spreading theory. And this is what is called the accretionary complex. So this accretionary complex is to create a new crust. So the seafloor bed of 200 million years can be also understood if you look at the accretionary complex. Sometimes the rocks which are found at the garden in Kyoto come from the thousands of kilometers away, traveling for like tens of millions of years. And so this is what we discovered. And after that, I went to the University of Tokyo, and I became involved in the research of Nankai Trough. So Shimanto Belt, what is happening at the Shimanto Belt is right now taking place at the Nankai Trough. So off the shore of the Shikoku, the Nankai Trough, looks like this. This is just a flat seafloor. It extends 4,800 kilometers. So there's some ridges and creeks, and you see some river-like structure. And if you further go up, along with this Nankai Trough, you will reach to the Fuji Mountain or Tagonora. This is just the foot of the Fuji Mountain. So let me play once again. So these are ridges. There are many ridges. And here seafloor is very flat. And you see some river stream-like structure. And if you go along with this, then you will reach Tagonora, the foot of Fuji Mountain. And here's the air gun, as well as the streamer cable. By using this technology, you are able to detect the structure of the seafloor. And the result of this research looks like this. So these are the ridges you saw. And here it's about 1,000 meters below the sea surface. And here is a strong refraction. And Nankai Trough is flat. It's because there are thick sediment layers here. And these ridges and crease like structure, then it will become a rugged structure. This was reproduced by this sandbox experiment. So plate, this is a Japanese archipelago, and here is a Nankai Trough. Then plate move from right to the left. Then those deposits are stacked, and so they form this kind of structure. And this is what is called the accretionary complex. So in the Nankai Trough, the formation of accretionary complex taking place, extending to the 1,000 kilometer, for example. So where do those deposits come from? Then the joyless resolution. This is the second generation after the previous vessel from the US that I mentioned. That is a global challenger. So this is a flagship vessel for international project. I went to a Nankai Trough 4 times to drill at the Nankai Trough, and one result. So this sand accumulated in a short period of time. So this is a layer of sand. At the bottom, you have a below lava, and you have volcanic ash based the mud area, and also the mudstone containing volcanic ashes. So this is exactly the same as the geological strata we found at the Shimanto Belt. And this sand, so on this sand looks like this. It contains many lightweight fossils. It contains a lot of the freshwater fossils.
And then where does the river start? It turns out that everything is sedimented from the one river, that is the Fuji River at the estuary of Mount Fuji. It traveled 700 kilometers, and this is the mudslide type of flow. The river, like Fuji River, because it is dense, so it doesn't scatter to the surrounding area. Because it is a steep river, so the sand will gush into the ocean. This is part of the Philippine sea plate, and there is a collision, and the volcanic archipelagos is on this side. And in the trench between the two, the river water flows in, and then there is a sedimentation creating a new land. So it is a massive natural civil work underway, and with the plate movement, this happens. This is the current process underway, and the Shimanto Belt had a similar phenomena millions of years ago. Underneath Japanese land, we have this accretionary complex underneath. And this is Nshino-shima Island, a new volcano. And this, at the beginning of the Earth history, there were collisions of the volcanoes, creating a chunk of land. And toward the end of the geological history, that collision continued and created the continent. So the Izu Peninsula collided with the main island of Japan. This was what happened in the first half of the geological history, and this is how the continent was developed eventually. By looking at the Izu Ogasawara area, we came up with this very solid hypothesis. So this is what happened. And joyless resolution was very successful with their missions. But when we did some operation in Japan, we found out some limitations. It was not able to dig deep enough. Japan is sitting on the 4 plates. So that is where the most active the plate movement is taking place. And we would like to contribute to the research of this very complex area, and we would like to have our new facilities in the deep drilling. And I came up with this kind of proposals working together with other colleague researchers in Japan and outside of Japan. And 11 years ago, we successfully constructed Chikyu vessel. This is the larger than JOIDES resolution, and it has a riser system that allows to dig much deeply. And there were only 3 other vessels with the same function, and the 2 were focusing on the drilling of the oil well. And after this, we are now able to do the deep water excavations. Currently, this kind of research is very popular, and however, still, the riser type of drilling vessel, the Chikyu, is the only vessel with that function. And we wanted to reach mantle. It is still our expectation. And also, we want to directly observe the source of major earthquakes. And more than 10 years ago, almost 20 years ago, we understood that the deep under the sea, underneath ourselves, there are microorganisms. We wanted to know more about the microorganisms deep under the sea. And the Chikyu was built, but there are a lot of difficulties. And I left Tokyo University and became a manager of this project and working for JAMSTEC. So now I am in a position to encourage others to do research rather than me doing research by myself. But the government grants and subsidies for research have been slashed little by little. And the marine research in the past 10 years, our current budget is 30 million yen, and that was slashed by 8 billion yen. And I was a manager of an organization, so I have to raise fund. And we did the deep drilling in Japan, but in Kenya, Sri Lanka, and India, Australia, there are researchers who get the fund and to do the drilling for the oil to get the external budget. But if we do this, we have to reduce the effort for the pure scientific research. And then, I am kind of criticized for that. But it is inevitable for us. We have to accept this fact because we need some money to continue our research. But still, we came up with the findings. One is off Tohoku area. This was done after the major earthquake in Tohoku region. The other is off Shimokita. The microorganisms, the submarine microorganisms, were explored. In 2011, March 11th, a huge earthquake and tsunami hit the area, and the Sendai airport was washed with tsunami. This was one of the biggest tsunami ever recorded in human history, for sure. And at JAMSTEC, this is the epicenter. And in this area, before the earthquake, we predicted that the Miyagi earthquake will take place here. So we repeated the observations. This is the research done in 1999, and this is after the earthquake in 2011. So we can compare these two. And what we found out was if you see this difference, this is the estuary axis, this is land area, and you see lots of yellow and red. The biggest is 50 meters difference. This means that the green is before the earthquake, and this is the topology after the earthquake. So the wall here, in a matter of several minutes, it moved as big as 50 meters. 50 meters movement is huge. This is beyond expectation in geology. This is such massive this ocean floor change. Not so a wide area, in a very focused area. And this is one of the reasons why we had such a big tsunami, which was very sharp. This is the tip here, and the trench 7,500 meters in depth. And if you dig here, and the tip that caused the tsunami, why moved as much as 50 meters? We could know the cause. That was an international proposal. And the Chikyu was damaged by a tsunami in Hachinohe, but we got there as a part of the international project. At Kyoto University's Professor Mori, was involved in this from the water depth of 6,800 meters and the fault at 820 meters. They discovered the clay layer, and this must be the source of the earthquake. Is it really the culprit of the earthquake? This is the circumstantial evidence, so there is no proof for that back then. So we used the temperature thermometer in the hole of 6,800 meters at depth. We thrusted the thermometer down deep. And because if there is an earthquake taking place there, there should be the friction heat. And even 2 years after the earthquake, 0.34 degrees thermal anomaly stays. By using the thermometer, we can detect this thermal change. And we observed for 8 months, and this portion, you see the red anomaly that was discovered. That shows the 0.31 degrees thermal anomaly. This is matched with the collapsed clay zone. So this is a proof that that place moved, actually creating the thermal frictions. So this is the fault we found out. This is a footage of that observation. In 2012, July 14th, so 1 year and 3 months after the earthquake, we visited this spot. This red thing is the thermometer. And now we put it in casing and bring it down to 6,800 meters in depth. Here is a fish. And once placed in the hole, it has to be cut. So the first step is whether we cut it successfully, and it is recorded by TV camera, and it was successful. So the crew were happy. This is Dr. Fulton of Texas A&M University. This was an international team effort. And then 8 months after, now JAMSTEC's the remotely operated vehicles, Shinkai 7000, went down into the sea. In December, there was a massive another earthquake, so we feared that the entire hole may be buried, but no, it was okay. And we confirmed that this is the drill pipe we embedded. And the thermometer's string, at the top there is a ring, so we used the manipulator to hook it up. We did it. The unmanned submersible were used to pick this up, so it is really the rudimentary operation. But the 7,000 meters in depth in this deep sea, we are able to do this because of our technology. And then it went up to the surface. And these are thermometers, and the recorder was the one we just showed you. And in Nankai Trough, we established a network of the seismological meters, and now at Nankai Trough, we can have the real-time notification system about tsunami. The warning can be issued as accurately as possible. The time and the place of the earthquake, I myself think that it is very difficult to predict, but we want to improve the quality of the real-time warning network, so we established this kind of system in Nankai Trough area. Just one last point to make. This is not so well known discovery. We dig the earth and we look at what's deep below the ocean floor, and the overwhelming majority of the microorganisms are actually deep below the ocean floor. And we know that by DNA sequencing, but we have not identified what they really are. Off Shimokita, we can dig up to 1,000 meters, and then we have a certain number of organisms. We know how many, but for the first time in human history, we dig 2,460 meters, and we detected a strange boundary. Beyond that, the number of organisms they abruptly decline. And then there may be the limitation of the biospheres around this depth. Why do we have this limitation at this depth? And some 20,000 years ago, this area's strata. So do these organisms sustain their lives for that long? Or is it the result of some kind of evolution? Or do they do something in deep under the ocean? We don't know much about it. But this was a paper in Science 2015. This has become a very hot topic around the world. And a team succeeded in the culture of microbes like the pasta like this. And some of them generating methane. And microorganisms are a generator of methane, and that is turned to methane hydrate. And it's easy to detect methane hydrate. We can detect them with sound. If there is a strong reflection, and then we can tell where the methane hydrate is. There is the lines. The methane hydrate exists above these lines. So the detection is quite simple. And off Atsumi, there was a project trying to produce the methane hydrate. With the JOGMEC and also the Energy Agency, we succeeded in doing so. And the natural gas was dug up. Of course, there are some technical challenges, but this is a pure methane. So the many things can happen in the future. Listening to Professor Kitagawa this morning, there was a whole. We could also use this technology combined with his technology. With the Chikyu vessel, the Chikyu was damaged by earthquake, but after the earthquake, Chikyu went to the epicenter area and did the exploration. And we succeeded to establish the network at the ocean floor to know more about the mechanism of the tsunami and earthquake. We have a better technology of the real-time prediction. But going forward, the research of submarine microorganisms will be the most important thing. When I started research, I have not imagined that the underground or under the ocean there are lots of organisms, but the thinking have changed so greatly. And now this is combined to the resource development of methane hydrate. The ocean drilling technology helps us to understand the ocean floor, expansions, and also interpretation of the Earth history. But the initial objective of digging deep is to reach the mantle. 50 years ago, the first vessel was developed to dig the mantle, but we haven't achieved this yet. The driving force of the plate tectonics, that is mantle, we do not know much about that yet. And also, there were the microorganisms in the flux inside the earth, and then there might be some new form of life we may be able to detect. That could be called mantle life, maybe. At least there should be some chemical evolution. Those are necessary for the birth of the life forms. Some of them might have come from the mantle. So, and the mantle is detached from the surface of the earth. If we find out the living form in the mantle, that should take a completely different shape or form from what we know now. And if there is a life form underneath, and then our understanding of the life system will be deepened. With this, we can create the new system and what will become of the Earth and what will become of the universe. We could have a better projections about that, and that will tell us what we should do right now. That's the end of my presentation. Thank you very much.